Continuing this series of videos examining conventional physics as explained or provided by Professor Lewin of MIT and such.
Earlier in this course we discussed linear polarization of electromagnetic radiation, and I demonstrate this at 75 megahertz and at 10 gigahertz. Today I will concentrate exclusively on the polarization of light, which is at a much higher frequency.
Alright, so yeah, maybe I'll draw a little because I didn't really, it's a subtle point but sort of important. So I have to hit this, I believe. Go ahead. Yeah, that worked. It might have worked. Might not be perfect, but it'll do. I mean, it'll have to. So I'm trying a new drawing system. Just get a little reflections for some dopey reason, but I'll fix that someday, eventually. So as pointed out, so in the radar experiment, he was pointing an antenna, a radar antenna. Oh, that certainly didn't work. Yeah. Let's see. Let's try this color. See if it makes a better line. So the antenna is a little 3 centimeter long antenna for these radar experiments, and the key thing was about the alignment of the antenna. And their conventional argument is that the current runs this way and this way, in a sense creating waves like this, as high as the antenna, so to speak. So these transverse waves, or however you want to, their description. And so you could sort of understand that if I was to put a grating in here, that as long as the grating is in the right direction, that is, I'm just going to draw it over here. The idea that the line's going this way, and the wave would be going in the same direction as the lines, and therefore wouldn't get blocked. And then if it was going this way, then the lines for the wave would get blocked because they'd end up hitting the bars and being absorbed, and so the polarization by their description. And so they have this kind of non-intuitive problem where their antenna is opposite the thing that works. This one blocks it, this one doesn't block it. Their transverse wave theory. So anyway, the point I would argue is that with conductors, the point I've tried to make is that the field is really coming around the circular. It's circular. It's probably a better way to describe that. So if this was a conductor, the magnetic field gave me an excuse to try some other color. This probably won't work at all, but well, it works better than I thought it would work. So essentially the field is coming out this way, plane with the conductor. So if the conductor was round this way, the field comes out this way. It doesn't go the length of it, it's coming out this way, out of the sides of the conductor. How to draw that? Well, like this, lines coming out this way. Yeah, not terribly visible either, so just fiddle around till we find colors that work. And this works for the reason I explained in previous videos, that it explains the right hand rule in the sense that that one's not doing much either, unfortunately. Let's see this one. No, doesn't make much of a line either. I don't know why. Yeah, got a ton of these cheap pencils. It's just some don't draw very well. Anyway, so like if you had a coil of wire, the field is coming out in these little, it's coming out of the sides of the wire, and it's by the right hand rule. The idea is that it's basically just creating magnets on the top and bottom of the wire. You could just think of the wire here And then what it's doing is it's creating a bunch of magnets that are in a row, and they're all divided, you know, north and south, you know, oppositely as they go around. It flips. So that's essentially your right-hand rule. And so when you have two conductors facing each other with the same current, that is, the current's moving the same way, they'll end up having magnetic attraction, because the magnets will essentially be inverted in terms of how they'll look. So they'll be the same, and same in this case means attraction, because it's this clockwise versus the two directions end up being one's going away, one's going towards, kind of thing. And so that explains that. And so I'm just saying that to be consistent with this theory of how the electric field emanates to create a solenoid, like I said, the field is coming out the sides of the wire. So it's coming out of this, you know, the sides of the thing. It's coming out this way in rays, and not going this way in any kind of wavy way. It's not waving up and down the surface of the wire. The little bits of magnetism are, it's north on this side, south on this side, from this point of view. From the opposite point of view, it's south and north. So it's radiating that same perspective magnetically, north, south, north, south, north, you know, north, south, no matter what side you go on. No matter what, how you spin around the thing, it'll always look like north on the right side, south on the left side. And so, I mean, that's, you know, that explains why there's these internal reflections inside a solenoid that creates this increase in the magnetic field inside versus out here. And so it explains why the wires attract when they have the same current. It explains the solenoid, and it explains a lot of stuff. So I'm just saying it. And you know, although the light is not the same exactly, it's going to fit this pattern. And again, their understanding of even radar, like I said, they're thinking it's doing this kind of, there's some kind of feature about it that has this waviness, and it's really not doing that. It's just the field is either there's either stuff or not stuff. So there's either something, nothing, then something, then nothing, then something, then nothing, in terms of the volume of the magnetic field coming out of the wire. And yeah, so let's see, this pen worked. So I had to figure out which ones work. This one worked? Yeah, this is a good one, the orange one. I put the orange cap on the blue one. Oh, okay. That will confuse me in the future. Blue one worked. Okay. So what would I want to further point out? So anyway, so in the previous video where he was talking about the radar, I should have pointed out that the reason why this polarizer works is that they're thinking the waves are going up and down. The waves are really going this way, and the lines, and so yes, they go through this filter unmolested, because their polarization is really side to side, you know, this way, not up and down. So the polarization is this way, not this way. Alright, so that's probably enough. And then this cap doesn't fit. That is an interesting phenomenon. Well, it's putting it on upside down. That's probably the reason. Alright. Not a total failure. We'll work on it. And so back to the videotape, as they say.
The light from the sun or light from light bulbs is not polarized. So I can ask myself the question now, what does it mean when light is not polarized? Let's think of individual light photons as plane waves with a well-defined direction of polarization. So each one is linearly polarized. A beam is coming straight out of the blackboard. The first photon arrives, it's linearly polarized in this direction. The second photon arrives, linearly polarized in this direction. So the electric field vector is oscillating like that. another photon, another photon, another photon, and another photon.
Right. So obviously, if these were waves, then you'd have to explain how they're coming in all kinds of directions. So when he said it's not polarized, the sunlight, he's really saying it's all polarized. It's just that the polarization is 360 degrees mixed, which adds up to, you know, it's polarized in every direction. So it's not like it's unpolarized. It's that the individual photons are all individually polarized in some plane. But it's all, when they're mixed, it's all planes of polarization. So it's like white light has all the colors in it. It's the same idea. You have all the polarizations in the sunlight, and only certain ones will be reflected back at certain circumstances, like with glare.
Photon. And what you see here very clearly, that there is no preferred direction when you average over time. And that's what we call unpolarized light. It was Edwin Land who in 1938...
So obviously I'd say that it's probably a wrong way to say it, because there probably is light that lacks polarization. That is, the light is very pure. That is, it doesn't have any polarization. The photons are emitted perfectly. That would be unpolarized light, if you want to be technical.
Developed a material that can turn this into linearly polarized light, for which he became very famous, in addition to this demonstration that I showed you last time.
Right. It doesn't really turn it into, it doesn't very literally turn it into, in the sense the polarizing filter does not detect its polarization. It actually does some converting. So anything within a range will be fixed. So everything that's, say if something comes through that's a little bit off, it'll be improved. Everything's improved that goes through. So it's like thinking about the frisbee going through the jail bars. Some of the frisbees can be a little bit off, and they'll be improved, some of them, by hitting the bar a little bit and be improved. So you're creating light that's closer to the same polarization. So the filter is fixing, in a sense, the polarization. It's creating polarization. It's changing the polarization. So when they use polarizing filters as detectors, you know, their measurement is clearly influencing the end result, the product. Clearly you will measure how many frisbees are within a range, but what you get as a product won't be the original stuff. It'll be changed stuff.
If I take one of Edwin Land's sheets, which will turn light into polarization in this direction, and I first take one photon.
So as I understand, it won't be perfectly in this direction. So it'll take 22 degrees and 22 degrees to make 44 or whatever degrees worth of light, and it will improve it to being within 10 degrees of the vertical. So it won't make it perfectly polarized in one direction. It'll take stuff that's quite perpendicular, quite opposite in this case. Perpendicular would be the opposite, and it will improve it. Obviously it works this way and this way just as well, top to bottom. This, you know.
For instance, this one. That one comes in from the blackboard towards you, and so here it is, oscillating the E vector like this. E0 is the maximum value of the...
Right, so he's saying it's oscillating this way. I would argue that the polarization just has to do with the alignment. There's no oscillating anything. Polarization just has to do with the alignment of the bits that make up the photon. So the more they're spread this way, coming at you, that's the polarization. So the polarization has a direction in the sense that the bits will be in an alignment, that they're getting moved as they're created by the individual electron that's creating the photon in the first place. That electron is wobbling, and as it's wobbling, it's creating polarization, but it's not creating anything like a wave.
Electric field strength in that plane electromagnetic wave. And this is the direction of the polarizer that I have through which this photon goes. I can now make a simple calculation by projecting this E vector onto the preferred direction of polarization. And this new E vector is now down by the cosine of theta if this angle is theta, this E vector is now E0 times the cosine of theta. If you ask me now whether the light is reduced in intensity, I would have to say yes, of course, because light...
So he's using a single photon example for a group photon experiment. So he's sort of grossly cheating here. Okay, he's not talking about individual photons now at all. He's talking about an average over a group of photons. And obviously, photons can't be diminished. They can't be split. They can't be broken. They can't have partial energy. And they don't have... The only thing that gives them energy is volume. Again, if you have more bullets closer together, it has more impact on whatever you're hitting, obviously. If the bullets are further apart, then in 1 second you can only get so many bullets in that 1 second, where if they're closer together you get more bullets. So you can change the magnitude of light by increasing its frequency, but you're really not increasing the magnitude of the individual bits. You're just increasing the number of bits. See, they haven't proven any of this wave theory. They're stating it as if we're pretty confident in this model, but the model doesn't fit. And the explanation, again, requires them to have very flawed analysis in the sense that they aren't analyzing individual photons, and they'll switch between individual photons and a mass of photons and just keep switching back and forth without making any statement about the fact that they're cheating again.
Intensity depends on the pointing vector, and the pointing vector is always proportional to E0 squared, because the pointing vector depends on the cross product between E and B. And if E is reduced, B is also reduced. And so we get a cosine square reduction. If now I average over all in...
So again, he's already averaged over all the photons. There is no decrease in either the frequency of the light or the intensity. All you're doing is saying some photons get through, some photons don't. So you're just saying how many photons will be permitted to get through the filter. And there's a certain percentage that will be permitted. 22 degrees, 22 degrees. That'll be permitted.
Coming photons. So I take all of these, which represent an unpolarized beam. So I get not only one like so, but I get one like so, and one like so, and one like so, and one like so. Then clearly, I have to calculate now the mean value of cosine squared theta. And the mean value of cosine squared theta is 1/2. And so if the intensity of the unpolarized beam, unpolarized light, was originally I0,
so he's just saying the obvious, which is half the light isn't going to get through. Half the light is not going to be in that 22 degrees. Half the light's going to be in the 22 degrees going this way. You know, 22 this way, 22 this way. The 44 degrees this way, that light isn't getting through. So half the light isn't going to get through the filter.
Once it comes through this polarizer that Edwin Lamb gave me, then I get 1/2 I0, but that is now 100% polarized, and it is 100%.
It's okay, so it's not 100% polarized in the sense that it's not all perfect, and but it will all go through another polarizer of the same orientation. So if I put another polarizer in front of it, these 22 this way, 22 this way, and that have now been improved to say 10 and 10, that'll make it through the second filter easy, no problem. But it will be completely blocked by a filter this way.
Polarized in this direction. And the 1/2 is the result of the average value of cosine squared theta.
No, it's the result of half the light is doing this, and half the light's doing this. The half that's doing this gets through, the half doing this doesn't get through.
If this were the case, it would be an extremely ideal polarizer. We would call this an HN50 polarizer. They don't exist, it's only in your head. And the 50 refers to the fact that 50% get through polarized.
So the catch is, as I've pointed out, that the polarizer is going to eat some of the light, some of the bars. So if I had jail bars and you're throwing frisbees the right way, you know, vertical, some of the frisbees hit the bar. It just happens. So some percentage of the right polarized light doesn't get through. all of the wrong polarized light doesn't get through, but some of the right also doesn't get through.
In the optics kits that we hand out today, that we will need throughout this course, you don't have HN50 polarizers. They don't exist. I don't quite know what yours is. I didn't measure it. Yours may be an HN25 or maybe an HN30, which would then mean that the I0 strength of an unpolarized...
So just understand how bad that is in a sense. Okay, it's a dramatic degrade as a filter. You're only getting 30 or 35% of the light. So 15% of the right photons have been destroyed, in the sense you can't see them in the form they originally were in.
Light of beam would not be half of I0, but maybe only 0.25 or 0.3. But in any case, the light that will come through your linear polarizers will be very closely to 100% polarized. So what I will do...
So again, 100% polarized just means it's pretty close. Doesn't mean it actually is every single one is perfect.
Now I will take unpolarized light, and I will have this light coming straight out of the blackboard, perpendicular to you, with strength I0. And here is one of my polarizers, and the light that comes through here is linearly polarized in this direction. And so we already know that 1/2 I0 will come through if it is an ideal polarizer, and it is polarized in this direction. I take a second sheet, an identical one. I put it also in the plane of the blackboard, but I rotate it over an angle theta. So here is now a second sheet, which has a preferred direction of polarization in this direction, and the angle is rotated over an angle theta. So between this one and this one is an angle theta. And so you can now immediately tell what the intensity of the light is that comes through this second polarizer. It must, of course, be polarized in this direction, because that is the allowed direction of polarization for that second sheet. And
so the point would be is that you've sort of improved this. Now you're going to change the bars to this. But the point is, most of what you improved will now make it through that second filter at 45 degrees. So you'll get most of that light will make it through the second filter.
Intensity must now be 1/2 I0, because that's what comes in, and then I have to multiply it by the cosine square of theta. I don't have to average it now over all angles, because there is only one value of theta between this sheet and this sheet. So
that's just doing the 45 would be 0.5, I guess, the cosine, say of a 45 degree angle, which was just you're cutting it in half. But obviously you're not, the key point would be is the half thing isn't happening, so you're still back to 0.3 or 0.4 percentage wise. So that's where this gets a little sloppy, is he's talking in terms of ideal polarizers, and those don't exist.
It's now the new intensity, and it's all polarized in this direction. And this law, whereby the light intensity is reduced by the factor cosine square theta, is known as Malus' law.
So again, that doesn't happen. If he had turned it 90 degrees, I mean, you know, the full 90, then you could argue, well, then all of it would be blocked. So yeah, never mind. It always goes that 22%. So well, anyway, I'll have to critters. Anyway, continuing.
Law. If theta were 30 degrees, the light intensity here would be 1/2 I0 times the cosine square of 30 degrees, which is 0.75. If theta were 0 degrees...
So that's 75 times 1/2. 75 times 1/2. Well,
That means that this sheet is in the same direction as this one. If everything were ideal, 1/2 I0 would get through the second sheet. If theta is 90...
1/2 I0. So he's saying 1/2 times it's supposed to be multiplied by 0.75. So how could it be 1/2? That doesn't make any sense.
90 degrees, then nothing will get through, because the cosine of 90 degrees is 0. We call that cross polarizers.
Yes, right. But that still didn't make any sense. Sorry.
Cross them like this, no light will get through. Now, before I demonstrate this, I have to be honest with you, because the idea of reducing the energy of individual photons by reducing their electric field strength, as I did, is a cheat.
So at least he's admitting it. Okay, this has nothing to do with their field strength. It just has to do with the number of photons that are going to get through the filter.
A light photon has a well-defined energy, which depends uniquely on the frequency of the light. Blue light has a higher frequency than red light. So blue light has a higher energy than red light.
Right, but they won't say it for the reason I just pointed out, which is there's more bullets in blue light because they're closer together, and that's all there is. The individual photon, if you took it as a bit per frequency, is exactly the same energy. You're just, with blue light, you can provide more energy in the same amount of time because the bullets are twice as close to each other.
And when you send blue light through a polarizer, the way I did here, it either comes through or it doesn't come through. But if it does come through, it is still blue light. There is no such thing as a reduction in energy. Whereas this reduction by cosine theta would imply that the energy goes down, and that would imply then that there would be a color change, and it would no longer be blue. And that's not the case. If you want to treat this properly, you have to do it in...
So the real cosine thing is what it's really doing. It's just giving you a percentage, which is good. So the more you deflect from the top, the more you start leaving out some of the polarization that's still not perfect. If the polarization was all perfect, then you'd have all or nothing again. You'd get to a certain number, and then all of the light wouldn't get through. Very, very dramatic. But it's obviously progressive based on the cosine. So that means with each little stage you move, you start extracting light. So that just means that the stuff that was, as I stated, it's still 10% uneven after it goes through the first filter. And what you're really saying is that this angle, the 5% on this side starts to get weeded out the higher your angle goes. So at this small angle, most all of it will be captured because it'll be within that 44-degree range. But as you go further and further down, you start cutting the imperfection off, and so only the stuff on this side will get through.
The quantum mechanical way. The interesting thing is that if you use quantum mechanics, you find exactly the same law. You find also Malus' law.
Yeah, well, there's no quantum mechanical interpretation.
So the law is okay, even though the derivation is not kosher. Now I want you to get out of your envelope one of your green plates, which is a linear polarizer. This is the kind of plate that you have. You have 3 in there. Only take 1 out.
I don't have one.
These 2 lights shining on me, unpolarized light. So the light that comes to you now is unpolarized. I'm now going to hold in front of my face this polarizer. So the light that comes through is linearly polarized in this direction. And you are going to play the role of the second polarizer.
So again, it's not polarized in this direction. It's polarized in a lot of directions that are close to that direction.
Close one eye, put the polarizer in front of your eye and rotate it. And you will see a huge difference in light intensity. If you cross-polarize with me, then you can't see me. That may make you very happy. But keep in mind, if you can't see me, then I can't see you either.
But you can see the proportionality. As you turn it slowly, it gets lighter and lighter and lighter and lighter. You see more and more and more because you're including more of those not perfectly polarized elements. If they were all one, then there'd be a point where you'd just wipe everything out. There'd be a point where you catch everything, and then there'd be a point where you lose everything. So clearly the light hasn't been completely perfectly polarized by the first filter. It's only been improved.
So rotate it around and convince yourself that this light that reaches you is now indeed linearly polarized. And when you rotate around your polarimeters, we call them polarimeters, we call them polarizers, you can see me either, or you cannot see me at all, and there's anything and everything in between. Very well. There's a second way that we can produce 100% linearly polarized light, and we can do that by reflecting unpolarized light off a dielectric, for instance water or glass. None of this follows from Snell's law. Snell's law was 250 years before Maxwell. Polarization wasn't even known in the days of Snell. But Maxwell's equations allow you to properly deal with refraction and reflection, including the polarization. And I will make no
yes, but only because they separate this magnetic component and this electrical component, and they have waves going this way. So again, their theory is completely backward to the facts, because again, they're still in the same problem in the sense that if they could actually see which way the the waves were vibrating, they'd see that their wrong filter is working.
Attempt to derive this for you in detail. That's really part of 803 if you ever take it. But I will present you with some results so that you can at least appreciate the far-reaching consequences of the reflection in which we can produce 100% polarized light. Suppose I have unpolarized light coming in. Here, medium 1 index of refraction N1, medium 2 index of refraction N2.
So unpolarized means mixed polarization.
It's coming in at an incident angle of theta 1, unpolarized. Some of it is reflected, and this angle is also theta 1 as we discussed earlier, and some of it is refracted into this medium, and this angle we'll call theta 2. So this light unpolarized comes in, reflects and refracts. If you want to use Maxwell's equations, at the action where everything is happening right here at the surface between the two, you will have...
So again, there's two surfaces, top and bottom.
Have to decompose the incoming light, the electric field vector, in two directions. And one direction is perpendicular to the blackboard, so this is the E vector, and the other direction is in the blackboard. You will have to do the same here, and you have to do the same here.
Alright, so none of that's necessary because there aren't two fields, there aren't two directions, none of that's happening. The light is coming in this way or this way, and depending on the polarization, it's more likely to reflect versus refract.
And if you look at this decomposition, then notice that both components, this component as well as this component, is perpendicular to the direction of propagation. That is always a must with traveling electromagnetic waves. You see the same here. This component and this are both perpendicular to the reflected beam. This component and this are both perpendicular to the refracted beam. This one,
to the direction of the movement.
the one perpendicular to the blackboard, we normally give a symbol perpendicular. We call this the incidence plane. The plane through the incident light and the normal to the surface, we call that the incident plane. In this case, that is the blackboard. We call this the perpendicular component, and we call this the parallel component. And this is, of course, the incident beam. So this one we call the perpendicular component, this one we call the parallel component, and this is now of the refracted beam. This is the parallel component, this is the perpendicular component of the reflected beam. The incident light is not polarized in this sense. So if you average, then there is no preferred direction of the electric field. That means then that in this representation...
So this is, again, not talking about single photons, but now we're talking about a massive different bunch of photons. And what is the photons? How are they going to be filtered by this process? So this isn't about what a single photon does. This is about what they do on average.
The strength of this component and the strength of this component must be exactly equal. Because if one were stronger than the other, then it wouldn't be unpolarized. Then there would be, on average, a preferred direction. So this component has the same strength as that component for the incoming light. What Maxwell's equations now can do for us, it's a lot of work, you may see it in 803, it can relate the parallel component in reflection with the parallel component of incidence, the parallel component of refraction with the parallel component of incidence. That gives you two relations, two equations. It can also relate the perpendicular component of reflection with this perpendicular component and the perpendicular component in refraction with this component. So you get four equations. If this light that comes in is unpolarized, the strength of this component is the same as this one. In general, you will see, if you apply these four equations, that that's no longer the case here. They're no longer the same intensity, and they're no longer the same intensity here. That means...
So it's just basically saying that in the reflected light, more of this stuff gets, stuff going this way, stuff polarized this way, as a higher percentage of reflection, and a higher percentage of the refraction is this way. So they're just changing the percentages, and as you as you steepen the angle, you guarantee more and more of that. And so when you have 100% reflection, well, when you have 100% reflection, you must have, yeah, it repolarizes the light. So it changes the polarization from mixed to entirely one polarization. So it's a filter that changes it 100%. Well, it changes the 50% to the other 50%.
Means this reflected light and the refracted light has now become partially polarized. I will only give you the relation, one of those four equations. I will only address today the parallel.
It's probably going to be that Brewster angle, so it'll end up be like 68 degrees or whatever the hell it is, where it becomes all polarized.
Component of the incident beam and the parallel component of the reflected beam. And I don't imagine that any one of you will try to remember that equation. I don't either. I have to look it up every time that I deal with this. So E0, which always represents then the maximum possible value of the electric field, of the parallel component of the reflected beam, that's the one that I'm after. I'm going to make polarized light by reflecting, is E0, the parallel component of the incident beam, times, and this depends now on the angle of incidence and on the indices of refraction. It's going to be N1 times the cosine of theta 2 minus N2 times the cosine of theta 1. Believe it or not, all of this follows from Maxwell, divided by N1 times the cosine of theta 2 plus N2 times the cosine of theta 1. And if you apply Snell's law, you can simplify this equation. In this case, it will help us. And so you get minus E0 parallel incidence, and now you get here the tangent of theta 1 minus theta 2 divided by the tangent of theta 1 plus theta 2. So these two equations...
that's sort of the small angle cheat in a way, but I don't know exactly why it's acceptable now, but whatever.
Are identical. So that may not be obvious to you, certainly not obvious to me either, but if you substitute Snell's law in here, you can show that these two are the same. Keep in mind, if you're ever interested in the intensity of this light, then you must always remember that the pointing vector is proportional to E0 squared. So you always have to square these numbers when you're interested in light intensity. This is just the strength of the E vector. There's something very special hidden in this equation, and that is when theta 1 plus theta 2 is 90 degrees, then the downstairs here is infinitely large. And so that means that
you have a complete reflection. Kind of, obviously.
The parallel component in reflection is 0. So E...
Well, complete refraction. So you don't get any reflection when you're straight. Is that what he's saying? Well, we'll see.
Parallel in reflection goes to 0. And if that one goes to 0, there's only this one left, which is not 0. And that means the reflected light is now 100% polarized in this direction because I have killed this component completely.
All right. So, yeah. So, again, they're doing the two, field thing. So he's saying one field of polarization is nothing and the other field of polarization is 100%. So, yes, it's what I initially said. You have a complete reflection.
But it only works if this is met, this condition. If this condition is met, that theta 1 plus theta 2 is 90 degrees, then it follows from high school maths that the sine of theta 2 is then the cosine of theta 1. That's immediately obvious, right? You remember the triangle. Theta 1 plus theta 2 is 90 degrees. The sine of one angle is the cosine of the other. And if now I remember Snell's law, which says that the sine of theta 1 divided by the sine of theta 2 is n2 divided by n1, I can replace now, only for this special case, the sine of sine theta I can replace by the cosine of theta 1. And so I get here now the tangent of theta 1. And so if this is the tangent of theta 1, that is under these conditions, then we have met the condition that I was looking for, that I end up with 100% linearly polarized light. And so this is the secret to getting 100% polarized light. And this angle is called the Brewster angle.
No, I was right. Okay. And it's going to be whatever, 57 degrees or something.
And so if we, for instance, look at the transition from air to glass, glass has an index of refraction approximately 1.5, depends on the kind of glass that you have. If I go from air to glass, which is what I will do in my demonstration, then the tangent of this angle is n2 divided by n1. This is glass, so this is 1.5, n1 is 1. Then you will find that the Brewster angle, theta Brewster, turns out to be about 56 degrees.
All right, so fairly close guess. Right, and so then you have 100% of the reflected light is polarized.
I can also make linearly polarized light by going from glass to air, by bouncing it off this way. Then, of course, I have to invert this, and then you'll get a Brewster angle, which is smaller, which is 34 degrees. But since I will do it with from air to glass, I want you to concentrate on the 56-degree angle. The way I'm going to do this demonstration, it's right set up here. We have light, a light beam that strikes a piece of plain parallel glass. That's all it is. There's nothing special about this piece of glass. So the light comes in like so, and here I have a piece of glass. This is the angle of incidence, theta 1. And so it's going to be reflected in this direction, whereby this angle is also theta 1. And something will go in here, that is that angle theta 2, which I don't worry about, because I want you to see that this can become 100% polarized. As this light comes in, it is unpolarized. This component and this component have equal strength. If theta 1 is 56 degrees or somewhere in that vicinity, this light is now 100% polarized. And I'm going to project that onto the screen, and I'm going to convince you that it is indeed polarized. You cannot use your own polarizers to see that, because the light in this beam is going to be 100% polarized. However, once it reflects off the screen, it no longer is, so you cannot use your polarimeter. So I have to use my own polarimeter to show you this. So if we can turn the light off there, of the overhead, thank you very much.
Yeah, so it'd be interesting to know how much of the light at the Brewster angle refracts.
I will turn on the light of my light beam. There it is, and I'm going to make it very dark for you.
This one assumes the refracted light will be also 100% polarized in the opposite plane.
So that we can see that very well. So the light comes in this direction, hits the glass, and the angle of incidence is now about 45 degrees. I purposely didn't make it 56 yet. I have here a large sheet of polarizer, one of Edwin Land's polarizers, and I will rotate that in this beam. You will see that it is partially polarized, not yet 100%, but it's already partially polarized. So there is already an imbalance between the perpendicular and the parallel component. So if I hold it in the beam and I rotate it, you will clearly see now that it is much fainter than it is now. And now I will go for the 50.
It'd be interesting to see the 30 degrees and the 20 degrees, because that'd be even, you know, it would have a bias, but yeah, it wouldn't be complete.
56-degree angle roughly. And so now I rotate my polarizer, and now notice I can kill that light completely. 100% linearly polarized. I may not have the angle perfect, but that's okay. You get the idea. It's very close to totally dark. Now you see the light. It's polarized in this direction, and now I can kill it. So that's quite a remarkable thing, that if we reflect light of a dielectric, that we can, at one angle and one angle only, which is the Brewster angle, that we can turn it into 100% linearly polarized light.
But obviously you can create it into 90%, 80%, 70%, and you know, right on down to yeah.
This does not apply to conductors. The behavior of conductors is very different from dielectrics, such as water and glass. You can use Maxwell's equations, of course, to study the reflection of electromagnetic waves of metals, but you get a very different result.
Yes, that'd be interesting, just to understand the difference between transmission mediums that transmit light and mediums that don't.
And so never expect to get linearly polarized light which bounces off metals. I have here, for your pleasure, a metal sphere, and I have a glass sphere, and if you still have your linear polarizers at hand, you can now, or a little later, just hold them in front of your eyes and rotate them around, Of course, you're not seeing light at the Brewster angle. The chances are that some of the light that's reflected off this glass, that you can clearly see that it's partially polarized. You can see a difference in light intensity as you rotate it. You're not going to see that off this metal. Now I come to a third way of polarization. There is a third way that we can make 100% linear polarized light by the scattering of unpolarized light.
Probably save this. So yeah, save that for next time. Yeah. So yeah, I think that's enough. I don't know if I have to add anything else. So till next time and such. I think.